Good morning. Welcome to Krishna's class. We begin with the third part of Lebesgue integral of bounded measurable functions on sets of finite measure. This concerns the convergence of sequences and the consequential convergence of their integrals. It's not something that is obvious, but one has to consider them in some detail. Okay. What is the problem? So that's what let us write down this problem. Before that, what you have is this, that E is R, measure of E is finite, and F is bounded. What have we proved earlier? We have proved that if, so this is what we know. If Fn is a sequence converging to F pointwise, then F is a measurable function. Now, what have we done so far? In the last lecture, we have considered this. We have introduced the integral of denoted by which is of course a scalar. And then we have found that if X is the class of all bounded on E, then X is a linear space, then X is a linear space. That would be, that's what we have proved. We have also proved that, okay, now what more we have proved? We have proved that integral over E of maps F to so X is mapped by integral to a real number. Then we have found that integral E is a linear function which is monotonic. This is what we have. Now the question that you ask is this, therefore this is what you have. You have x here, you have r here, so the integration is a map from here to which is a linear function. It's a linear function which is also monotonic. Now one of the questions that you naturally ask is the following. We have seen that if Fn then pointwise convergence exists is an element of integral over E x. Therefore, what is the question? So let us now write down the So the question that you ask is the following. does integral over E now this amounts to the following, that is limit of n tending to infinity integral over E is this equal to integral over E which is equal to so the problem that you have here is, can this limiting process jump inside the integral? Okay? Or is the limit and integration interchangeable? Now let us recall that this question we have asked in the case of Riemann integration. The answer to this question for Riemann integrable functions with the Riemann integral in place of integral. That is Riemann integral replacing Lebesgue integral is not necessarily true. In general, that is, one cannot assure No, this cannot be. That is the interchange of the Riemann integral with the limiting process is something which cannot be assured. And that's why, I mean, these are all some of the inadequacies that we have observed with the Riemann integration, which in turn made mathematicians to do something or go for a more general version of it, where these kind of drawbacks are addressed. Okay, so this is question, right? So this is the question that we are addressing with. So what we are going to prove is that in the present scenario, that is on X, okay, this interchange is possible. If you assume Fn converges F to F pointwise. Okay, so that's the. So here, of course, the example that we have looked at is this Q intersection 0 1 we write as given enumeration Q1 etc. It's a countable set of rational numbers, so you can enumerate. And now if you write Qn to be this collection, look at Fn defined by characteristic function of Qn then chi Qn converges to pointwise. But you know that not Riemann integral. Whereas these chi Qn are Riemann integrable functions, but their limit is not a Riemann integrable function. Therefore, no question of this integral being true appears, because the limiting function. So this function is not even Riemann integrable. So this integral does not exist. Okay, so that we shall just keep it in mind. And you can see that if I were to replace this by Lebesgue integral on 0 1, then you see that this interchange is valid. However, integral over the above example. Integral over this is it. So at least as far as this particular case is concerned, our the new integral that we have has the property that the integration, the limiting process can be just changed. Okay, at least for this example. Now the natural question is it in general true? Okay, so this is our problem. So the central problem that we are going to address is this. So the problem is valid or this is the question that we ask. We examine this in detail. So first we assume, how do we go about doing it? You strengthen the condition of convergence. We are talking about point-wise convergence. Now we first consider a stronger form of convergence, namely uniform convergence. And we prove that if there is uniform convergence, then this result is true. So first we prove that this result is true is possible if a stronger form of is assumed. Namely, uniform convergence. That means we assume that on X, we look at all sequences Fn which converge uniformly to some function on or some element. In fact, it's some element of X, because you know that uniform convergence was note that implies point-wise convergence. So that is true. Okay, therefore we state the theorem. This is the statement of the theorem. Let bounded measurable functions on if this is the condition converges uniformly on E. So F integral over converges to integral. So under the assumption of uniform convergence, this result is true. I think one can easily do this, do much work, but then what is important is that you need such a strong condition that we will examine. Now we'll go through the proof of this for understanding the proof of the more general result. Okay. F is a measurable bounded function because we have seen that even pointwise, this is because uniform convergence and we have already seen that under pointwise convergence F is bounded and measurable, therefore in the special case it is more so. Now let epsilon positive arbitrary then choose n such that measure for every such an n exists. Okay? Such an n exists. On account of uniform. Now we estimate the two integrals. In all this, what is important is to understand the question. Once you understand the question, then you can work your way to. In this context, we ask, is it a sensible question that you ask? And if so, what do you get? What inference you make out of it? Does it have an answer? Okay. Now, by linearity and monotonicity, integral over take the absolute value of this. This is equal to absolute value of and this is less than or equal to the previous theorem, integral over E mod and this is less than or equal to epsilon okay. Is equal to. So here measure of E is finite is being strict. Okay, so we have used the fact that measure of E is finite. The very fact that we can choose n like this is because we use this measure of E is finite. And that implies limit n tending to infinity. This is the point. This is the uniform limits that you look at. So that completes the proof. Okay. So under very strong convergence criteria, namely uniform convergence, the result holds. But we know that even if I don't assume uniform convergence, I simply assume point-wise convergence. See that the limiting function is something that is a bounded measurable function on E. Okay. Therefore, you naturally ask, is this such a strong condition required to prove this theorem? So the question is, note that even if assume only pointwise numbers. So the question is this. So let us ask, whether the result holds good even when uniform convergence is relaxed to pointwise convergence. Replace the condition by pointwise convergence. That's a question that take up. So we shall prove that it is indeed this is possible. Under some restrictions. Okay. It's not necessarily a bounded function unless you assume the functions are bounded. So what do we have to assume? Okay. So let us look at the example. Get some insight. Now let us consider this function. For each, or we take e to be for each natural number be defined by equal to 0 for x greater than or equal to by n, and this Fn at 1 by n is equal to n. We assume Fn 0, and see the graph of such a function Fn. So you mark this as also mark this point as 1 by n, this as 2 by n. Now at the function be n, and then essentially it is the joining of 0 0 with 1 by n n. This point is 1 by n, this point is 0 0, this point is 2 by n 0. So this is linear, this is also linear, and 0 from here on. So this is the function. So the graph of the function is this. This is your Fn. That is it. Now you see that, observe that not bound. The sequence Fn is not. Each individual Fn is not the entire sequence. That means if you put an m positive, you can always find an n bigger than m such that Fn is not less than or equal to. Okay. So it's not bounded, right? Now converges to F pointwise almost every F take as identically 0. Because as n goes to infinity, you see that it starts becoming 0. You see that if it is pointwise almost everywhere, then of course limit of the sequence is f identically equal to 0 almost everywhere. And therefore, what you have is that 1 equal to integral 0 to 1 f or limit n tending to infinity of integral fn on the interval 0. That's easy to compute because it is the area enclosed here. The area enclosed here is always equal. And then this is not equal to okay. So what have we done? We have tried to replace uniform convergence by simply pointwise convergence. But pointwise convergence does not assure that the limiting function is a bounded function. So even if these functions fn are bounded, the limiting function is not necessarily a bounded function. Therefore, by simply replacing the convergence, uniform convergence by pointwise convergence is not likely to satisfy this. Okay. So what do we do? What is the problem here? The problem here is that the functions, the sequence of functions fn do not form a bounded sequence. Okay, right? Although each function is a bounded function, but it's not uniformly bounded. So observe that uniformly pointwise. This is one problem that we observe. Whereas when we assume uniform convergence of bounded measurable functions, assured that the limiting function is also bounded. So once we replace this by a more general sort of convergence, namely pointwise convergence, then you cannot assure that the limiting function is a a bounded function. Okay. Therefore, for such functions, we have not introduced integration at all so far. Okay. Right? Okay. So what do? We now put an extra assumption, namely the functions converges, the sequence of functions converges pointwise on E, but not necessarily uniformly, like the functions that we have seen. Secondly, we assume that the we relax the condition, but when we assumed uniform convergence, it was automatically a consequence of that the limiting function is also a bounded function, which you are not getting here. In this example, we have seen it. Okay. Therefore, we have to assume that. So for that, what we replace uniform convergence by pointwise convergence. Now you see the interchange of limit and integration may not work. The previous example shows that the limiting function may not be bounded. Bounded, and hence the integral not defined of such functions. So we strengthen this of pointwise convergence with the assumption that the sequence Fn is uniformly pointwise bounded. Pointwise bounded. Still not as strong as is not still as strong as the uniform. Okay. So let us, so this leads to, this is the well known bounded convergence. So just write down the statement of it. So let us make the statement of the theorem. Let sequence of measurable functions on a set of suppose the sequence Fn is uniformly pointwise bounded. It is there exists such that greater than or m so the uniform bound of this is given by this. Now if So this is the uniform boundedness theorem. So let us just recollect what have we done. We are not going to assume that the convergence is uniform. Instead, we assume Fn converges to F pointwise. Then we found that if we just work with that assumption, may not get the interchange of limit and integration, because we have seen that example where the function is not, the sequence of functions is not uniformly bounded. Each function is bounded, but the whole collection is not uniformly bounded. And in that case, you see that the theorem fails to hold. Okay. So let us replace. So what we need is, we need an additional assumption. The additional assumption is this, that Fn is uniformly pointwise bounded. With that assumption, you see that once again the result. So it is not as strong as the uniform convergence that we have assumed. If we assume uniform convergence, all this is assured. Okay. Therefore, we will just prove this theorem now. The proof. So here, what we use is the Egger's theorem. What does the Egger's theorem say? It says that the convergence, the pointwise convergence on E is nearly uniform convergence. Okay. So we can use that fact and then make use of our experience on working with uniform convergence to prove this here. So that is the strategy. Okay. So proof. So recall that Egger's theorem assures that the pointwise convergence implies nearly uniform convergence. Nearly uniformly convergent So, although it is point-wise convergence that we are assuming, it shows that it is nearly uniformly convergent. And what do you mean by that? So, we shall use this fact. Now, the point-wise limit denoted by F is measurable on E and mod F is less than or equal to M, since mod Fn is less than or equal to M, uniform. That is what we have assumed is that this one. Yes. Some such that this is true. Therefore, the limiting function is also bounded by this uniformly bounded, or the limiting function is bounded. Okay. So now we do the following. See, this is something which you could not assure in the absence of the assumption that Fn is uniformly bounded. It's only because of uniform boundedness of Fn that we are able to conclude that F is also uniform. Let A be any then by linearity and additivity over domains of integer This means that if A intersection B is empty, then integral of A union B is equal to integral of A plus integral of, that is the condition that we are talking about, integral over E this is equal to integral over A slash A so we designate this by star that we need to use. Okay, now using this we can get some estimate, general estimate in terms of the measure of price. Integral modulus of integral over this is less than or equal to f over A plus and that is less than or equal to integral over A mod f1 minus f plus, see that f1 is uniformly bounded by m, therefore f is also uniformly bounded, so you get m plus m, the measure of E slash. So this is the result that I want to designate by star. So now we choose A. By Agraph's theorem, there exists a measurable subset E such that for many epsilon positive such that Fn converges uniformly. In fact, A is a closed subset. Okay. Fn converges uniformly on A, and measure of less than epsilon by four. So that is possible. That is what the conclusion of the Egloff's theorem. Okay. There exists a closed subset A to E such that this is true. Now you see F is measurable bounded by M on A. That is what the theorem says. Therefore, there exists M such that mod Fn minus F epsilon divided by 2 into measure of B this is on account of the uniform convergence of Fn to F1, right? Consequently, just a minute. Epsilon divided by twice measure of B multiplied by measure of B A, you can put measure of B. So plus 2n into measure of, and this of course is less than okay. So for each epsilon positive you can do this. Okay. Therefore so this is the theorem that we have proved. So you have seen the type of conditions that replace this uniform convergence. Uniform convergence is replaced by uniform boundedness, and the first point wise the convergence is relaxed by assuming only pointwise convergence. Okay, so with an additional support, if you relax pointwise, if you relax uniform convergence by pointwise convergence, the theorem. So this is what is called the uniform model, which simply shows that example shows that without the support of some such additional assumptions, the theorem does not. That's it. So remark, just put it across again. Additional support assumption the theorem may not be, does not hold. By pointers. As you will see. Remark 2, the second remark that we want to make is we have used the countable additivity of Lebesgue. Countable additivity. In disguise. This is done we have fallen back on a gross theorem. Which uses it. See, until this point we did not use this one. Okay, until proved the bounded convergence. Not used countable additive. We require only finite additivity finite additivity. Until we know cross. So recall these little things because you should know where we are using the countable additivity, where we are using the finite additivity. So that completes the discussion on the Lebesgue integral of bounded measurable functions on sets of. So one remark I want to make at this stage is this. See, we are systematically progressing. We first proved the integration or introduced the concept of Lebesgue integration for simple functions and then use that to go to the next level. So each time what you have done is the problem of introducing Lebesgue integral for bounded measurable functions on sets of finite measure has been reduced to the use of Lebesgue integral for simple functions on sets of finite measure by invoking the power of what is called the simple approximation theorem. Okay, so that's something that has to be followed. Now we use all these results to go to the next level. That means we relax conditions like the assumption that we are working on sets of finite measure, and we even assume that we are not necessarily assuming the functions to be bounded. Okay, right? So we replace it or relax those conditions. Next stage. I'll make more remarks about it as we discuss the next level of generalization. Thank you very much.